Welcome to the public hearing for the Versatile Test Reactor Environmental Impact Statement. My name is Tom O'Connor. I am the Director of the Versatile Test Reactor Program for the Department of Energy's Office of Nuclear Energy. In this presentation, I'll describe the mission need for the project and provide an overview of the key features of the Versatile Test Reactor, or VTR. The next speaker will present an overview of the National Environmental Policy Act process and the VTR Environmental Impact Statement, or EIS. Both presentations will be available on DOE's project website at the URL included in the announcements for this meeting. That URL will also be provided at the end of the presentations. First, we'll cover background information. The mission of DOE is to advance energy, environmental, and nuclear security of the United States, and also to promote scientific and technical innovation to further that mission. One of DOE's strategic objectives is to explore advanced concepts in nuclear energy that may lead to new types of reactors with further safety improvements and reduced environmental and proliferation concerns. In addition to supporting the development of advanced nuclear reactor technologies, the Office of Nuclear Energy is also responsible for sustaining the existing commercial nuclear power fleet and reestablishing our nuclear fuel infrastructure. DOE's existing test reactor infrastructure is currently focused on fuel and materials testing for thermal or low-energy neutron spectrum reactors, and does not have the capability to fully support the development of advanced reactor technologies that can provide improved safety and efficiency benefits, or the ability to conduct greatly accelerated testing of materials applicable to our existing fleet of light water reactors. Understanding that the lack of accessible fast spectrum testing capability is a serious threat to U.S. leadership in worldwide nuclear innovation and safety technologies, DOE's Independent Nuclear Energy Advisory Committee, or NEAC, surveyed the needs of the U.S. nuclear user community, which includes DOE programs, universities, and U.S. advanced reactor developers. With the shutdown in the 1990s of the Argonne National Laboratory's Experimental Breeder Reactor 2, or EBR-2, in Idaho, and the Hanford Fast Flux Test Facility, or FFTF, the United States lost its dedicated fast neutron irradiation testing capability. This capability gap, documented in the NEAC study, has created the basis for the VTR program mission need. The United States needs domestic fast neutron spectrum testing capability to test advanced nuclear fuels, materials, instruments, and sensors in prototypic environments for successful development and deployment of advanced nuclear reactor technologies. For long-term commercial advanced reactor operations, a test reactor is needed for continuous technology improvements. After all, innovation isn't one and done. Decades of innovation in commercial light water reactors and in the United States naval reactors have been made possible by DOE's Thermal Spectrum Advanced Test Reactor at the Idaho National Laboratory. This thermal test reactor has tested innovative ideas resulting in superior naval reactor performance and lifelong cores, and in contributions to operating capacity improvements in commercial light water reactors from fleet-wide averages of 60% in the 1980s to over 90% today. Advanced nuclear reactor technology leadership and long-term innovation requires a fast spectrum testing platform. Congress has shown bipartisan support of regaining U.S. leadership in the development of new nuclear technologies. This bipartisan support is demonstrated by many major pieces of legislation in recent years, including the 2017 Nuclear Energy Innovation Capabilities Act, or NECA, which was signed into law in 2018, as well as the Energy Act of 2020. NECA amended Section 955 of the Energy Policy Act of 2005 and directed DOE to assess the mission need for a versatile reactor-based fast neutron source with an aggressive schedule that would lead to facility operations as early as December 2025. DOE acted quickly to launch the VTR program in 2018 with the first year of budget of $35 million, followed by $65 million in fiscal year 2019. In February 2019, DOE formally confirmed the need for a fast spectrum test reactor. Late last year, Congress enacted the Energy Act of 2020. This legislation, within the Consolidated Appropriations Act, further amended Section 955 of the Energy Policy Act of 2005 and directs the Secretary to provide a fast neutron testing capability and authorize the necessary funding and revise the completion date from 2025 to 2026. The mission need discussed previously is translated into purpose and need in the EIS. The EIS evaluates reasonable alternatives, including one or more action alternatives that meet the purpose and need. DOE's purpose and need for taking this action is to provide a domestic, versatile, reactor-based fast neutron source and ensuring the availability of associated facilities that meet the needed requirements. The associated facilities include those for the preparation of driver fuel, in other words, the fuel that powers the reactor. Other facilities needed include the ability to fabricate experimental fuel and material specimens, the fabrication of experimental sample holders and test rigs, as well as facilities to perform post-irradiation examinations. So as noted previously, since the 1990s, the United States has not had a viable domestic fast neutron testing capability. Reestablishment of this testing capability as an integral part of the U.S. testing infrastructure is needed for the development of the next generation of nuclear reactors. VTR would help us develop the fuels, materials, and instrumentation that would enable nuclear energy to expand its role beyond just electricity production. VTR would give us the conditions needed to conduct accelerated testing to support rapid development of innovative technologies. VTR would help the United States regain and sustain our global leadership in this emerging technology space, which is essential to protecting our interests, along with those of our allies, when it comes to nuclear safety, security, and non-proliferation. The lack of a versatile, fast neutron testing capability is a significant strategic risk affecting the ability of DOE to fulfill its mission to advance nuclear energy, environmental, and nuclear security of the U.S. and promote scientific and technological innovation. The proposed action is for DOE to construct and operate the VTR at a suitable DOE site. DOE would use existing, expanded, or new facilities and capabilities as necessary to most efficiently accomplish the VTR mission. These facilities and capabilities would be used to support a wide range of VTR-related activities, including fabrication of VTR driver fuel and experimental test vehicles, and managing radioactive waste and spent nuclear fuel, and facilities for the post-irradiation examination of the fuels and material samples. So what is VTR? VTR is a test reactor for the development of advanced materials, fuels, instrumentation, and sensors to support continuous innovation for different types of advanced reactors, as well as highly accelerated radiation tolerance testing of materials used in existing reactors. The VTR conceptual design is a sodium-cooled, pool-type reactor with a power of 300 megawatts thermal. It is designed to meet certain DOE requirements. Those include a large flow or flux of high-energy neutrons, large testing volumes, the ability to test in different coolant environments, because advanced reactors may use sodium, lead, molten salt, or other coolant materials, and the ability to accommodate multiple users, since the legislative directive is to establish a user facility. From a reactor perspective, VTR is larger and an improved version of the previously mentioned test reactor, EBR-2, that operated at the Argonne West National Laboratory site in Idaho from 1964 to 1994. It is also important to note what the VTR is not. VTR is not a breeder reactor, and DOE would not recover any nuclear material from the spent fuel. And VTR is not a power reactor, so it would not produce electricity. This slide depicts the conceptual design of the VTR. Key features of the VTR: the reactor is sodium cooled, operating at nearly atmospheric pressure and reactor outlet temperature of 932 degrees Fahrenheit. The reactor vessel is approximately 18.83 feet in diameter and is surrounded by a guard vessel that is approximately 19.82 feet in diameter. Passive heat removal is provided via the Reactor Vessel Auxiliary Cooling System, or RVACS, which consists of 4 pairs of stacks naturally circulating air for the removal of decay heat from the guard vessel. RVACS is in continuous operation and is designed to safely remove decay heat from the core under all scenarios. Executing the proposed action, building VTR on such an aggressive timeline, will require a strategic approach to avoid first-of-a-kind challenges. It requires the use of a proven technology with a high degree of technology readiness and extensive operating experience. It requires leveraging existing technology to significantly reduce the design time, and it requires the use of a proven driver fuel in order to avoid the development of a new fuel, which can take decades. And it requires a well-integrated design and construction schedule, sequenced in such a manner such that critical components have been prototyped and the design completed before construction is commenced in order to minimize risk. This slide depicts the conceptual site layout. It's pretty small, about 25 acres. The cooling is provided by 10 mechanical air heat exchangers that are about 100 feet tall. All of the reactor is underground with support facilities above ground. If this were sited at the Idaho National Laboratory, it would be adjacent to the Materials and Fuels Complex, about 29 miles west of Idaho Falls. The hot cells and other laboratory operations in the Materials and Fuels Complex would support the VTR operations, including post-irradiation examination of test items and treatment of the spent fuel. If the VTR were sited at the Oak Ridge National Laboratory, it would be located at a site previously considered for other projects, about a mile east of the ORNL main campus and about a mile northeast of the high-flux isotope reactor. A new hot cell building would be constructed adjacent to the VTR to provide the VTR support activities. A key consideration for any reactor, especially for a new type of reactor, is what kind of driver fuel to use. There are many technical and practical trade-offs involved. Some fuel types would not provide the neutron flux needed to achieve the goals of the VTR program. Considerations examined the availability of feedstock material, previous irradiation and operational performance, and impacts on reactor size, safety basis, and cost. We've selected a proven fuel type for initial VTR operations. That is, a metal fuel alloy composed of uranium, plutonium, and zirconium. This driver fuel type has previously been used in EBR-2 and has been tested in FFTF and has a proven and well understood irradiation performance history. The availability of the raw materials from which to fabricate VTR fuel is also an important consideration. DOE is investigating the use of its stockpile of excess plutonium, primarily from the dismantlement of nuclear weapons. This source should be sufficient to supply the VTR for its expected life. There is also excess reactor-grade plutonium available from several international sources. Depending on the plutonium-239 content of the reactor-grade plutonium, it would require the use of uranium enriched from 5 to 10%, whereas weapons-grade plutonium could be used with uranium less than 5% or currently commercial available enriched uranium. The VTR project is planning from the start to responsibly manage driver fuel removed from the reactor so that it can be readily be transported off-site as soon as an off-site facility or repository becomes available. The VTR spent fuel would not be recycled to recover any uranium or plutonium. Used fuel would be moved from the reactor core to temporary storage locations within the reactor or cooling for approximately a year, and then placed in heavily shielded casks for another few years, approximately 3. After that time, the fuel would be transferred to a hot cell near the VTR, where the sodium in the fuel pins would be removed and the fuel melted and cast into metal ingots. These ingots would be placed directly into the casks that are expected to be suitable, as is, for disposal in a deep geologic repository. This process builds upon the lessons learned from managing previous test reactor spent fuel and establishes a process up front for safely managing the VTR spent fuel. Spent fuel ingots from 60 years of operation could be stored in fewer than 40 casks, pending off-site truck shipment. Interim cask storage would be at the VTR project site and would occupy less than half an acre. Thank you very much for your time and attention. Much more information on the Versatile Test Reactor is available on the DOE website listed here.